Hi and welcome back to Module 6, Acid and Base Reactions. Today we are looking at how the definition of an acid and a base has changed over the last number of decades and how we think about acids really now. So there has been a number of different changes over the years with regards to the definition, and our first one actually started with Robert Boyle. So he defined acids and bases just really in terms of their observed properties, but nothing really according to their chemical composition. That came along with the following scientists. So we've got Lavoisier, Davy, Arrhenius, and Bronsted and Lowry. So if we look at our dot point here, we have to mention the last two, but we're not limited to those. So we are going to look at the contributions those earlier scientists have made. So our first one here, Lavoisier, he thought, and it worked out that it was incorrect, that all acids actually contained oxygen and that was what made them acidic. And he kind of found that when like carbon dioxide, for example, was dissolved in water, it did produce an acidic oxide. But as with most theories, that was later disproved. But he was that first scientist to actually try and define an acid by its chemical structure. So then we had Davy. He actually worked out, or decided, or tried to work out the composition of hydrochloric acid, and discovered that it was actually a compound of hydrogen and chlorine and actually didn't contain any oxygen, which actually then went to just disprove the previous theory. He also worked out, as we've just done in some reactions as well, that metals could actually displace the hydrogen from that acid, and it wasn't actually the oxygen did that. It wasn't a complete definition, but it was certainly an improvement on what we'd had previously. So then we come along a little bit further, and as our theory goes, we are becoming a little bit more developed in what we think. And Arrhenius, he suggested those acids are neutral substances that dissolve in water and that they will dissociate to form their positive ions and their negative ions, and name them our cations and our anions. And he used that to define the acids and the bases. So if you look in the picture that we've just got here, we have got hydrogen chloride. So it would dissociate H plus and Cl minus with a water. And when it actually went into solution, one of those hydrogen atoms would attach to the water, forming a hydronium ion. So that would be written as H3O plus, and a chloride ion on its own. So his definition then was that an acid is a substance that ionizes in water to produce hydrogen ions as the only positive ions, and that hydrogen ion can join to water to produce that hydronium ion, and a base ionizes and dissociates to produce those hydroxide ions. So it was quite useful, but it did have some limitations that our next scientist worked on. So the problem with this model was it only applied to aqueous solutions, so it didn't actually work with our gases. So for example, our ammonia, when it reacts with acids, it doesn't form that hydronium ion or whatever. There's no hydrogen ions or hydroxide ions that were there in solution, so that kind of discounts that theory a little bit. And it only accounts for substances that already have the hydrogen or the hydroxide in their structure. And there are some substances that are actually amphoteric. They can act as an acid or as a base, and it doesn't account for that one either. So the Bronsted-Lowry theory attempts to develop that theory a little bit more and account for those differences. So this is not just one person. It was two scientists that both independently came up with this theory, and both obviously deserve the credit. And this happened in 1923. And according to that theory, an acid-base reaction is when a proton is transferred from the acid to a base. And so the new definition is an acid is a substance that donates a proton, and a base is a substance that accepts the proton from the acid. And that overcame those limitations. So we will look into this a little bit more because our module inquiry question 2 actually does look at the Bronsted-Lowry theory in a little bit more detail, but he came up with the fact that there were conjugate pairs. So he said that every acid has its conjugate base, and that conjugate base would have one proton less than the conjugate acid. So if we have a look here of some examples of some conjugate pairs are H2O. If we lose one of those protons, it would then become OH. HCO3, its conjugate pair would just be the CO3, 2-. It's lost its H. And with the same with all of the others. H2PO4, its conjugate base is HPO4. HSO4 would just be SO4, and so on. And thanks for watching. We'll talk again soon.